And now it's time for our Astronomy Minute. Ron, you're still on, I see.
Yes, I am.
Are you ready?
I am, and with any luck, my screen should be sharing.
I see it.
Let me get this up because I think this is what everybody's interested in for right now and get that out of the way. So I figured that doing a little fill-in tonight with the Astronomy Minute that it would be appropriate to cover what is a meteor shower and why is it appropriate? Because we're right smack dab in the middle of the Perseid meteor shower, probably one of the most popular ones of the year. Now, for those of you who are new to meteor showers, a meteor shower occurs when the Earth passes through a stream of debris left by a passing comet. There is at least one meteor shower that occurs when the Earth passes through debris left behind by a passing asteroid, but some scientists think that that asteroid might be the remnants of a dead comet. But anyway, the vast majority of meteor showers occur when the Earth passes through that trail of mostly dust-sized to pea-sized debris. And that surprises a lot of people. They think, well, gee, a meteor shower is going to produce meteorites and you got big rocks floating in space. And it's actually really not that. Figure dust size, sand size, maybe pea size or a little bit bigger as the Earth passes through that. And we see that as a meteor shower. There are about 64 confirmed meteor showers and another roughly 300 that are being studied. The table on the lower right of the slide shows a few of the more popular ones that some of you may be familiar with, and they occur throughout the year. And of course, we're in mid-August right now, and that's home to the Perseid meteor shower. Now, most meteor showers are named after the constellation from which they appear to originate. That point in the sky is called the radiant. And as you look at the little graphic in the upper right part of the slide, you can see the radiant for the Perseid meteor shower is near the constellation Perseus. So as I just mentioned, Perseus is the radiant for the Perseid meteor shower, and the Leonid shower, which occurs in November, appears to originate in the constellation Leo, and so on. And I need to point out something important here. Meteor showers have nothing to do with meteorites. They do not produce meteorites. Remember, the meteoroids that produce those visible meteors, the streaks of light we see in the night sky, are no bigger than dust to perhaps the size of a pea in the vast majority of cases. All right, well, how the heck do you observe a meteor shower? Well, best time to observe most meteor showers is between local midnight and dawn. This is also true for this year's Perseid meteor shower, as is the case with the vast majority of meteor showers. And what you want to do is find a place that's away from bright lights. If your backyard is reasonably dark, that's okay. But if you can get to a location that's got a very dark sky, that's even better because it will allow you to see the dimmer meteors that are going to be obscured by either the city light or even moonlight. So make sure you're dressed appropriately for the weather. If it's a chilly time of year, you're going to want to bundle up. If it's a warm summer time type evening, you're going to want to dress for that. And of course, in the summertime, you may also want to prepare for any critters that might get in the way, maybe bugs or something else. But anyway, be prepared for whatever is going on at the time that you're reclining. Now, here's my favorite way to observe a meteor shower, and that's to take a reclining lawn chair and fold it back flat, all the way back, and then look more or less straight up. You'll see some people say to look at the radiant. My preference is to look more or less straight up because you can see more of the sky with your peripheral vision. If you look just at the radiant, you're more likely to see just the shorter meteors in the sky. And if you look more or less straight overhead, you're going to get a mix of the short ones and the long ones. And sit back and enjoy. And an important point about meteor showers, you do not need binoculars. You don't need telescopes. You just use your eyeballs. So the Perseids, that's the one that's underway right now, appears to radiate, as I mentioned earlier, from the constellation Perseus. This shower peaks each year around this time, around August 12th, and as I noted, it's a favorite of a lot of shower observers. The parent body of this is Comet 109P Swift-Tuttle, so the Earth right now is passing through debris left behind in space by that comet. Now, the peak of the Perseids actually occurred this morning. It was around 7:20 a.m. Mountain Time, and the best time to observe it was last night between midnight and dawn, at least if you wanted to see the peak. But the good news about the Perseids is that it produces visible meteors for up to 2 weeks before the peak and 2 weeks after the peak. So if you missed the peak last night and early this morning because of the weather, when I went to bed last night, it was overcast. And when I got up this morning, the sky was kind of iffy. There is a way that you can see, actually hear meteors in the sky. And you go to this website, livemeteors.com. That's the one I had on the screen at the beginning, and I'll show you that here in a second. So I'll wrap this up with a photo from NASA. It's a time exposure of the Perseid meteor shower, and you can see those streaks of light. The streaks of light are the meteors, and those all appear to originate from the constellation Perseus, so right about there. So let me get out of that and bring this up. And there is that site I mentioned, and you can probably hear a little bit of hiss in the background. I've been monitoring this for the last hour or so, and I've heard maybe a half dozen meteors, and they sound like a little ping, a little tone. And what that is radio waves bouncing off of the ionized trail left in the upper atmosphere by the passing meteoroid. And the service that provides this, and it's free, has radio receiver located somewhere on the East Coast, and they're tuned to a frequency coming out of Canada. And when a meteoroid passes through the upper atmosphere and produces that meteor, which ionizes a column of air, then radio waves from that distant radio signal bounce off of the meteor trail, and it's received by the receiver that's connected to this website. And you hear this little kind of a tone, and it's called a meteor ping. So that's the presentation that I've got for tonight's Astronomy Minute.
Thank you so much, Ron. That was very interesting. Now I got to go do that when I get home. Listen to some meteors. All right. So next up is, oops, sorry, wrong button, is our main event, our guest speaker. So Mehmet, are you online? Are you prepared to introduce them?
Sure. Our guest speaker this evening is Dr. Elizabeth Fernandez. Dr. Fernandez has a Ph.D. in astronomy from the University of Texas, where she studied the first stars and early galaxies that form in our universe. After that, she worked on how observations from various telescopes, from Herschel to Hubble to LOFAR, can tell us about the star formations in the early universe. She is currently a science writer, writing for various places like Sky and Telescope, Space.com, Discover Magazine, Physics Magazine, and many others. She loves telling the stories of astronomy, geology, physics, and mathematics, as well as how science impacts society. Her complete work can be seen at sparkdialogue.com. So, Dr. Fernandez, please proceed with your presentation.
Okay, well, thank you for that introduction. I'm really excited to be here virtually with you all today. I actually had my start as an amateur astronomer myself, which is not something every professional astronomer can say. And actually, when I was in high school, my local amateur astronomy group was really instrumental in helping me, develop my love for astronomy even more. And so I was really happy to see your outreach events going on, and I hope that I see the good work you guys are doing with that. And you never know the impact you might have on some young lives. So I'm very happy today to be here, like I said, and I am going to talk about the very first stars and galaxies that formed in the universe. This is something that's really difficult to observe, but it's something that's very instrumental because it helps us to understand how the universe is formed like it is today, like why we see the things we see today. So to begin this story, of course, we have to begin with the beginning. It's not something we can take for granted. This is the universe started with the Big Bang. And at this period of time, we had protons and neutrons forming very early, and a few minutes later, those combined to form atomic nuclei. And the point of me showing you this slide is I'm sure you know the Big Bang, but also it's important to remember that there was a long period of time in the universe where there were no stars. There was not a lot of structure formation forming yet. There were no stars, there were no galaxies. And so something had to happen to change this, to get that first star going, to get light in the universe. And so that's the story I'm going to talk about today. So if we want to try to understand how this change came about, we can look back as far as we possibly can. But the thing is, we can't see all the way back to the Big Bang. There is a limit to how far back we can see. And this is because the young universe, after the Big Bang, it's very, very dense. It's a sea of photons and electrons and protons. And these photons, when they are in this sea of very dense particles, they can't actually just travel like they would in today's universe. They bounce off free electrons, which are these red dots. So the photons are the blue arrows. And so you have this light, it just keeps bouncing off all of these electrons. This makes the young universe opaque, which means we can't actually see all the way back to the Big Bang. But as the universe expands, density and temperature begins to fall, and eventually it cools down enough that the protons and electrons begin to combine. This is an event that's called recombination. And when this happens, all these electrons are no longer there to scatter the photons anymore. So the photons can now freely travel to us. This is called the surface of last scattering, because it's the last time that a photon can scatter off an electron. And so we can actually observe this. This is the yellow strip in this slide. So the surface of last scattering, you probably better know it as the cosmic microwave background. So this is the farthest back we can see in the history of the universe. This is like a snapshot of the baby universe when it was about 380,000 years old. And like I said, we can't see beyond this with light. And so this image here is the entire sky. So you can imagine that this is a globe, and we're in the middle of this globe, and it's kind of spread flat. So it's like a projection of a map that this is what we're seeing. And there are some areas that are redder, and there are some areas that are dark blue. And these represent slight different temperature changes between these two areas. This is like a glow from the Big Bang, you can think of it, that is at a very uniform temperature, which is about 2.7 Kelvin. But the areas that are slightly red and the areas that are dark blue, the hot and the cold areas, are actually really, really close. They're very, very uniform in temperature. And the difference between these areas is only about 10 microkelvin. Now, when you think about this is actually pretty phenomenal that the entire sky can be so uniform from completely opposite sides of the universe, how we're seeing it. But yet these small fluctuations that we're seeing are going to become the seeds of the first stars and the first galaxies. Then they eventually become this, what we see. We see galaxies everywhere. We see structures on all sorts of scales. We see gigantic, huge clusters that spread millions of light years, but we see structures on, the size of our solar system. So the first question that we want to ask when we are looking at evidence of the first stars is, how did we go from this very, very uniform universe that is very similar in all directions to one that has just a complete richness of structure on all different levels? So by asking this question, this can begin to help us understand what the first star's role was in this. Now, the second question I want to bring to your mind is looking at how star formation affects its environment. So this is an image of a nebula. This is a part of the Carina Nebula. And this is, of course, in our local universe. But it gives you an idea of how star formation affects the environment around it. So in this image, you have these gigantic towers of hydrogen gas with dust, and they are formed and sculpted in all these weird tower-like structures by baby stars that are turning on, and as they begin to send out light and radiation and stellar winds, they begin to carve these crazy things that we're seeing in these towers. So this shows you that is a very visual way to understand that stars affect subsequent generation of stars. Like everything is interconnected when these things are forming. And so when you are looking at these first stars, though, if you imagine the first star, there is no subsequent generation of stars before that. So all of these processes that you're seeing in this picture, this beautiful picture here, you won't be seeing for the first generation of stars. So imagine that these first stars, they formed with no radiation or any other effects from previous generations of stars. They're forming out of this pristine gas that is just gas. We don't understand exactly what processes are going on exactly at this point in time. But one thing that is important to realize is that these first stars will only have hydrogen and helium. And if you think about stars around us, if you've ever seen a spectrum of the sun, for instance, you see lots of elements that are present in the sun. And a lot of these elements are elements that are left over from previous stellar generations that formed in supernova or in fusion within a previous generation of star, and that these are present in our sun. So our sun is what is called a population 1 star. Population 1 stars have lots and lots of elements that are heavy. They have carbon, they have oxygen, they have silicon. And we, of course, know this because we formed out of the stellar nebula. Our Earth is here. It has lots of elements in it. You wouldn't get planet formation around a population 3 star. It just wouldn't happen. Population 2 stars are stars that have a little bit of heavier elements, but they're a lot more metal poor than what we would see in our sun. So, for example, stars within a globular cluster are often population 2 stars. And these stars, these first stars that are forming just out of hydrogen and helium, they're what we're going to call population 3 stars. They're formed out of no elements except hydrogen and helium. Okay, so why is this important? The reason why is when you think about a star forming, a star, in order to form, actually has to cool down. It seems kind of counterintuitive, but when you think about a gas cloud collapsing, it needs to lose some of that energy that we see as heat in order to collapse to a point where fusion can start. And elements, heavier elements, help gas cool and help it fragment into smaller clumps. If you don't have these heavy elements, the gas can't cool as effectively and it can't fragment as easily. So what might be the result is that these first generations of stars might be very, very big. I mean, here we have our sun, we have Aldebaran, which is a red giant, and other stars that you might be familiar with. Well, a first generation star might dwarf all of these. They could be very, very massive. And of course, if a star is very massive, it's probably very, very short-lived. The bigger the star, the quicker it burns through its fuel. But I mean, we don't know for sure, though. I mean, this is a big question in trying to understand the first stars that formed. Where some people suggest maybe they're very similar to what we see in our, as far as mass, see in our local universe. But some people suggest that they might be hundreds or even thousands of times the mass of our sun, or maybe even larger. And I'll talk a little bit about those possibilities more in a moment. So all of this is important when you talk about when this population 3 star dies. it will further affect its environment by its stellar remnant. Okay, so when a star dies, what happens? Well, that depends on the mass of the star. So for very small stars, like the mass of our sun, or relatively small stars, it'll at the end of its life, it'll become a white dwarf. Slightly larger stars will become a neutron star, and even larger will eventually explode in a supernova, and then that leads to a black hole. So these three possibilities we're all pretty familiar with in our local universe. But if you have a very massive star with very, very few heavy elements in it, there's some other interesting possibilities that begin to pop up. One is it could directly collapse into a black hole without going through a supernova phase. So it collapses so quickly that everything in the star itself gets tied up in a black hole. If this was to happen, then none of the elements that it formed over its lifetime through fusion will get out into the interstellar medium. So that means it doesn't enrich the area around it, and you'll continue to form population 3 stars for longer because no elements are escaping. Another interesting possibility happens when you have a very, very specific massive star. It's between 140 and 260 solar masses or thereabouts. And when the star is very low with heavy elements, it's called a pair instability supernova. And what happens in this situation is, in a normal star, you have gravity that is pushing the star inward. But the reason why stars don't collapse is because they have fusion going on, and that fusion gives a lot of pressure from the photons that are making their way out of the star. So that holds the star in equilibrium. But what could potentially happen in a pair instability supernova is that the central temperature is high enough and the pressure is high enough that photons begin to convert into electron-positron pairs. And this causes the core to collapse. Fusion starts to run away, and the entire star completely explodes, and leaves absolutely no remnant. This is exactly the opposite of a direct collapse black hole, because everything formed in that star will go out into the interstellar medium at this point. Everything will go out to enrich the interstellar medium. So this leads to our second question. This means that all these stars, all of these generations of stars, somehow can affect the subsequent generations of stars through metals and through radiation. And so this is our second question we can try to attempt to answer when we're looking at these, looking for evidence of these first stars. Finally, another thing I want to talk about is an event that we know happened very early in the history of the universe. Okay, this is a little picture of a hydrogen atom. So I mentioned that at the cosmic microwave background, we had recombination, where all of the protons got together with their electron, and they formed a hydrogen atom. The whole universe was like this. Well, if you start forming stars, though, something can happen. A very energetic photon can come in and ionize that hydrogen. And so now we do not have a neutral hydrogen anymore. Well, very early in the universe, something happened that ionized every single hydrogen atom in the entire universe. And this is called reionization. This is an event that we know happened. And in order to get reionization, you need a lot of ionizing photons. You need a lot of very energetic photons to ionize every single hydrogen in the entire universe. And so what provides ionizing photons? This must be stars. And so this could be our first stars. And so, for example, here's a kind of some snapshots of what the universe might look like over time. In the far left, you have the lighter blue is kind of the neutral hydrogen, and we have stars begin to form, and they form these little bubbles around them of ionized hydrogen. And as these stars continue to put out ionizing radiation, these bubbles grow. More and more stars form in these galaxies, and the bubbles grow even more until finally we reach the end of reionization, and the bubbles overlap. All the hydrogen is ionized. So we know this happened, and so this is our third question. how can we address this event that happened? Okay, so now I'm going to shift a little bit from talking about our questions to how we can actually observe these first stars and what kind of evidence we can look for to try to figure out what they were like. Okay, so one way to look for these first stars is to look for them directly. Look for the most distant galaxies we could possibly see. So this is a image from JWST. This is one of the most distant galaxies that we have ever seen. It formed 290 million years after the Big Bang. So this is when the universe was still in those very early stages when it's forming these early stars. And you notice the galaxy itself is very, very red. This is because as the universe is expanding, the light that it is emitting is stretching with this stretch of the universe, and we actually see this as red because it's becoming longer wavelengths. And this was seen earlier this year with JWST. We're beginning to see more and more of these very, very distant galaxies, and these can help to tell us more about what these stars were like. This is a really amazing observation that was made also by JWST earlier this year. First of all, let me explain how this image was made. So on the left-hand side, we have a cluster of galaxies. And clusters of galaxies are incredibly huge. They have a lot of mass. And when you have a lot of mass, you will deflect the light that is behind it. And you can deflect it, and you can also amplify it. So it acts like a giant lens. So these clusters of galaxies can look like, imagine light coming through your glasses or light coming through your telescope. These whatever's behind it can be amplified, but also distorted. Okay, so then you look on the right-hand side, you see this really long red arc. This is actually one object, and it's called Earendel. Astronomers think that this is actually an individual star. This is amazingly far away. It's 900 million years after the Big Bang. It's 28 billion light years away. And the fact that we can see an individual star at this amazingly vast distance just blows my mind. But looking at this star, scientists believe that it's anywhere between 200 or 20 to 200 solar masses. So it could be many, many times the mass of our sun. So these observations exist. We might get more of these observations with time, which would be awesome. The next thing we can look at, we can actually look in our local universe for evidence of population 3 stars. Now, how this works is that I mentioned earlier that if you have a very massive star, it has a very short lifetime. It burns through its nuclear fuel very quickly. On the other hand, if you have a very small star, the lifetimes of these stars can be very, very long. Some can be longer than the age of the universe. So it's possible that if you had a population 3 star that was very small, it could still be alive today. So scientists are actually looking for these stars. Now, it's very hard to find these stars. This is a globular cluster. This is an example of one place that you go to find very old stars. And so to find these old population 3 stars, people look potentially in globular clusters, but also in very, very small galaxies that are nearby, maybe in the outer edges of our own galaxy. So far, no one has found anything yet, but it is possible that people might have seen a second generation star. So that means ones that formed with just one generation of stars before it. And I'll talk a little bit more about that later on too. Okay, one more observation that we can make is to look at what's called the near-infrared background. Now, I've talked about the cosmic microwave background. That's the light that's all over the sky in the microwave. There is a similar background in the infrared, in the near-infrared, that we don't understand where it comes from. One idea is that this background could be, at least in part, from these very early stars. Because if you imagine these stars are big, they're bright, they emit lots of ultraviolet photons, as the universe expands, these ultraviolet photons get longer and longer wavelengths, and we will actually observe them in the infrared. So if this is true, how much of this light is actually from first stars and first galaxies? The nice thing about this observation is that if you're seeing all of the stars and all of the galaxies that are contributing to the infrared, they don't have to be big and bright and showy like the ones showing up in the JWST pictures. They're everything. It could be just an individual star. It could be a very, very small galaxy. So this could be one interesting way to get a full sample of everything that's going on. Now, another observation we have made is that there are very, very large black holes very early in the history of the universe. For example, very recently, astronomers have found a black hole on the order of a few million times the mass of our sun. And this black hole is in place in the universe only 400 million years after the Big Bang. So personally, I believe this is one of the biggest questions in astrophysics today, is how in the world do you get these gigantic black holes in place that early in the history of the universe? Now, if you think about, let's say you have a star that's 100 solar masses, and it dies and it becomes a black hole. Even if you have it merging, if you have this black hole merging with other black holes, or if you have it accreting as much gas and dust as you could possibly throw at it, it is virtually impossible to grow it to a size of a couple million times the mass of our sun by the time we're seeing these black holes in place. So this is a big mystery, and this is one that potentially looking at the first stars and galaxies can address. All right, and another thing we talked about earlier is to look at this epoch of this time where the universe was reionized, when all of the neutral hydrogen became ionized hydrogen. Well, one way we can potentially observe this is to look at neutral hydrogen. So on the left-hand side, we have a hydrogen atom, we have the proton and the electron. They both have this quantum mechanical property called spin. You can kind of envision it like it's spinning around like a top. If an atom has both the proton and the electron spinning in the same direction, it has slightly more energy than if the proton is spinning in the opposite direction of the electron. So if the atom moves from this higher energy state, where they're both spinning in the same direction, to the lower energy state, we emit a 21 centimeter photon. So a photon with a wavelength of 21 centimeters. So by looking for this photon that's in the radio band, we can actually try to see neutral hydrogen. All right, and one last observation we can make, which is a really interesting way to look for these first stars, is by looking at gravitational waves. So gravitational waves are something that you get when you have, for example, you have two neutron stars or two black holes that are orbiting each other. And as they begin to orbit and as they begin to collapse into one object, it's such a dramatic event that they actually ripple space and time itself. And these gravitational waves stretch and compress space, and they can stretch and compress space all the way to where we are today. And there have been several observatories that have been built to try to find these events that happen. And there's been a success in finding a lot of these events happening. Now, the interesting thing about gravitational waves is that this is a completely independent way of observing our universe than what we're used to. Most of our telescopes, well, all of our telescopes except for these gravitational wave ones, are looking at the electromagnetic spectrum. They're looking at the infrared, they're looking at visual, they're looking at X-ray or radio or whatever. These are all part of photons that are reaching us. But gravitational waves are something completely different. This is a new way to look at what's going on in the universe, which I think is pretty nice to have multiple ways to see what's going on. Okay, so we have all these observations. So what have we learned so far about these first stars? We can put all of these observations together and we can see what we can learn. The first is that population 3 stars probably were the dominant star up until about 100 to 200 million years after the Big Bang. So, for example, if you imagine time going to the right, the red stars are, or the red dots are population 3 stars, and they begin to form. And as they die, they begin to enrich the spaces around them with elements, and those are shown as the blue regions. So any star that forms within this blue region would then be a population 2 star. And as these regions begin to grow and to merge, eventually the population 3 stars begin to get crowded out, and we see less and less of them as it becomes more like stars we see in our local universe. The next thing we've learned is that this is through a lot of simulations that people have done. So this is a simulation of a star forming out of a very early gas cloud. And these stars probably actually formed in groups. Now, this isn't immediately obvious because as a young star, or as a young star with not many elements to make it break up into smaller pieces, scientists didn't know if these stars were going to form as one giant massive star by itself or many somewhat smaller stars. But it seems that simulations are beginning to point to the fact that they are probably forming in small groups of like 5 or 6 stars. The next thing I want to say is that it's really hard to directly observe these distant stars and galaxies. Here's another example of another very distant galaxy that we have seen. This is when the universe was 430 million years old. Now we're all of these observations are incredibly important, and we're always very lucky when we get a picture like this. However, it's important to remember that these galaxies that we're seeing in these pictures are some of the brightest galaxies that exist at this period of time. The dimmer galaxies we're not going to see; they're just too dim. And also, if there are very rare galaxies, we're not going to see those either because we only can observe so much of the sky at once. Or it's possible that it's just a matter of luck. Something just happens to be behind a gravitational lens, and that's what's magnified. So these observations are very important, but it's important to remember that they are limited. But it might be actually easier to try to observe star formation happening in even smaller galaxies through looking at the 21 centimeter background, which is in the radio, to look at the neutral hydrogen before the stars ionized it, or through gravitational waves. Now, on the left-hand side is a picture of the radio telescope LOFAR. It is an array of antenna that starts in the Netherlands and kind of radiates all throughout the Netherlands. And one of their goals is to try to find evidence of these first stars beginning to form and to ionize the area around them. Okay, so the question, how big are they? This is a really interesting question. So very recently, there's been some evidence of a second generation star, so a star that formed with only one generation of star before it. And the reason why they believe this is because they believe it might have formed out of the remains of a pair instability supernova. When you have a pair instability supernova, it gives a very, very distinct chemical signature. It has this odd even effect when you're looking at atomic number. So here on this plot, you have atomic number, so all your elements are lined up, and on the y-axis, you have the abundance of these elements. And as you can see, they kind of form this zigzag pattern. There's a lot of one element, the next element there's not as much of. This is the elements that are present in this star. And this matches the possibility that there was only one generation of star before this, and it was a 260 mass star that eventually ended its life in a pair instability supernova. Now, this is a very, very early area of research, so it's still very controversial, but it's interesting that potentially they might have found potential evidence of this. On the flip side of this, we still haven't found any population 3 stars around us. So that could mean that they just weren't that small. They haven't made it till today, or we might have been unlucky, which is also possible. But we also need at least some mid-range stars, and these are stars that help to create our the diversity of elements we see. I don't know how well you can see this, but this is a periodic chart. It was on Astronomy Picture of the Day at one point, and it shows the where each of the elements that we have in our periodic chart, where it comes from celestially. Some come from low mass stars, some come from high mass stars, some come from supernovas or radioactive decay or whatever. But in order to get this diversity of elements, we need a diverse sources for these. And then finally, it's possible that there might have been some very, very, very large stars. And this goes back to the black hole question. Now, there's also been some sort of controversial findings of potentially very massive stars that existed that could potentially, at the end of their life, they collapse directly and they form the seeds of these supermassive black hole we see. And some people suggest that these stars could be incredibly large, maybe up to 10 to 100,000 times the mass of our sun, which is mind-boggling. But it's possible that these stars directly collapsed, and it's also possible that these stars weren't true stars how we think of them, that they might have not really had fusion like we know, but they might have just collapsed in such a way that they might have gone through a very short time of fusion, or maybe none at all. Again, this is still a very new area that we're still trying to figure out. But all in all, these stars are pretty special. They're pretty unique. They might be really big. They can help us form these giant black holes we see. But perhaps most importantly, at least for us, is that they help to set the stage for the universe that we see today. They help our elements and radiation form so that newer generations will form, and so eventually planets like Earth can form. And so, thank you. That's what I have for tonight. And if you have any questions, I'll be happy to hear any.
Thank you, Dr. Fernandez. This was a very, very, very interesting presentation. I have actually several questions, but I'll ask one just to trigger it. So what you are saying is one of the main cause for black holes might be the population tree stars, if I understood correctly. So maybe the reason why we don't see population tree stars right now around us are because they might have been converted to or evolved to black holes. The question I have is, what is the determining factor for black hole sizes? Are there various parameters for determining the size of black holes?
So first of all, not every star will form a black hole. Because if that happened, we would have no elements that go to form.
What I meant is population tree. I think you implied that population tree stars might have led to.
Yes. So some of them might have become black holes. That's correct. Yeah. Okay. So your question is, what is the masses, or what determines the masses of these black holes?
Yes.
Yes. Okay. It basically comes down to two things. One is what happens when the star first dies. Okay. So I had a slide where there's two ways black holes can form. One is it goes through a supernova and then it becomes a black hole. When it goes through a supernova, it will lose part of its outer envelope. And so just a fraction of the mass of the original star will become a black hole. On the other side, the star might completely collapse into a black hole, in which case its initial mass of the black hole will be the same mass as the star, essentially. But then after the black hole forms, it'll go through this period of time where it can grow. So it can grow two ways that we know of. One is to merge with other black holes. So then that's essentially potentially doubling its size every time it merges with something. Or it can accrete gas and dust as fast as it can. from the neighborhood around it. And so both of those things will help grow a black hole. Does that answer your question?
Yes, yes. Why are these stars called population 3? I would have thought that it would start with population 1 as opposed to population 3. Was there a reason for the sequencing of the stars?
It's the same reason that astronomers name anything. They knew about population 1 stars first, because that's our sun. So that was population 1. And then when they find population 2 stars, they're like, okay, what do we name these? And so on. And population 3 stars are actually fairly new coming along. So population 1 and 2 stars were named a long time ago. And then so just how a lot of things are backwards in astronomy. It's just another example of that.
Okay, thank you.
Yeah.
I'll let other people ask their questions.
All right. Do we have any questions in the room?
Okay, I can remember in the process of searching for population 3 stars. Okay, I can remember I read a book, I think it was called First Light, and that's what it was all about. Essentially the search for population 3 stars, and what they concentrated on, it seemed like they were talking about the hotter stars, like at least class G and up. Okay, hotter than that. But however, with the lifespan of trillions of years, why don't we consider the possibility even of red dwarfs, for instance, being population 3 stars? Or does that go back to your argument that without the heavy metals, red dwarfs could not have formed?
So they absolutely could have formed, and that's one thing we don't know. The one line of evidence against that is that we haven't seen any that are still alive. If they have very, very long lifetimes, long enough that they could still be alive, we could potentially observe them. And we haven't seen any. And people are looking; they're looking very hard, but they haven't found anything yet. So that's one. I mean, maybe one day they'll. Yeah.
Okay, yeah, so I presume that whatever red dwarfs are considered to be population 2 stars, at least. And
The ones, yeah.
And we'll be here for trillions of years after we're gone.
Exactly. So that's the line of evidence. I mean, I know several people, that's their life work, is to look for very, very small dwarf population 3 stars. So they might be out there. We might just haven't found them yet. But so far, people have not been successful in finding them.
Okay, thank you.
All right. Let's take one from online. David Grant asks, do we think galaxies came together as stars formed?
Yeah, that's a really good question. And that is one that we don't quite know the answer to yet. That comes down to the question of, do stars form in groups or do they form by themselves? And this is a really hard question to answer, because when you're talking about these very, very first stars, the very even farther back than we can see, like with JWST or anything, it's possible that stars formed by themselves before they started forming in galaxies, or they formed in very, very small groups. But when you're asking these questions, so far what we had to rely on is looking at simulations, because this is the only way we can get answers right now, because we just can't observe it. It's just too far away. And so simulations look like that they form in small groups, but not necessarily in galaxies as we would think of them. And this probably would happen as time goes on. Their groups begin to grow to larger and larger sizes.
Thank you. Do we have a question in the room?
Hello, my question concerns the reionization event.
Uh-huh.
First off, where along the timeline do we think reionization happened and with respect to the Big Bang? And then also, is there a theorized catalyst to that event?
Okay, so I didn't hear the last part of your question. If someone could repeat that, just the last part.
Yes, I was also asking, was there a theorized catalyst to the reionization event?
Okay, so the catalyst is you need a lot of very energetic photons, and so these energetic photons most likely came from stars, because stars are one way that you can just pump a lot of really energetic photons, and so that's why there's this tie-in with looking for first stars and looking for reionization. And as to when it happened, that's another question we don't quite have the answer to yet, but it's probably on the order of a couple of hundred, maybe 500 million years after the Big Bang, to about 1 billion years after the Big Bang, in that range. But that's just something that that observations are hopefully will answer within the next decade or so.
Thank you.
Mhm.
All right, Bill, you have your hand up.
Yeah, can you hear me?
Yep.
Yes.
Okay. I can't remember the name of the type of nova, but it's the one, the really massive stars that go thermonuclear and they don't collapse into a black hole, leave nothing behind. Have these novae ever been observed directly?
That's a great question. So it's called a para-instability supernova, and no, they have
Yeah,
not
that's
been.
the one.
Yeah, they have not been observed directly, and so it's still pretty controversial that they even exist. The chart that I showed just a couple slides back, this where'd it go? This is one of the first evidence that people have that one actually happened. This one of looking at this chemical signature, this odd even event, this odd even pattern of elements is pretty much the only evidence we might have that these things existed. But as far as observing it, like an actual supernova, we have not been nearly that lucky.
You'd almost have to be looking for it and know it was coming, and then there's nothing left, no evidence left behind. It's crazy.
Yeah, you would have to be pretty lucky to see something like that.
All right, Dr. Bickle.
One of the questions I would have is with a new star, really old, is there work indicating how big the star has to grow to get to the point it can fuse helium? Obviously, if it's a little star, it's going to just go through what it's got and burn out. But if it obviously got bigger, it could get hot enough to fuse helium. Is there a no break point there?
Sorry, could someone repeat that? I just have a hard time hearing it. Yeah.
Okay. Is there a known break point with a new star? How big it has to get to reach the point it will fuse helium? In other words, a lot of the suns that we look at, they've got a lot of heavy metals. There's that CNO cycle that's running. But in a new star where there is no metals, is there a known break point how massive it has to get before it can begin to fuse helium?
Well, there are stars that are fusing helium even in our local universe. And there are stars that are fusing heavier elements as well. It just depends on how massive the star is and where it is in its life cycle. I'm not sure if that's answering your question, but yeah, I mean, this is stars can fuse anything up to, what is it, iron, and before it can't fuse anymore. So the more massive stars, the more it can fuse with time.
All right. Mike Jenizik asks online, what new observation tools need to be developed to observe population 3 stars?
There are so the one some of the most promising ones I think are looking at the the radio to look for the 21 centimeter line. So that's looking for the neutral hydrogen. That's part of reionization. So there are a lot of places that are coming online soon that will do this. For example, LOFAR is the one I mentioned, but there's also one in South Africa called Meerkat, and there's half a dozen other ones that are, most of them are going to come online within the next decade, and they're very, very new, a lot of these. And then a lot of the gravitational wave observatories that are going to be coming online as well, like LISA, for instance. These will be able to find very distant events that are happening, and potentially very distant events that are happening, to understand like how massive these if there's two very, very massive black holes and they happen to collide, we'll be able to potentially see that event, and that will help to solve a lot of questions as well.
Hello, is it possible to make repeat observations of a star like Earendel, or is that a one-shot deal?
I think I don't think time is something you have to worry about in that type of observation, because nothing has moved. The star is still there, the cluster is still there, so it's not something that's varying with time. So with that, we're just lucky as far as space. They just happen to be aligned in space. So yeah, so we can go back and take more observations and maybe get better observations in the future. That would be great.
All right, Dr. Insay.
Yeah, I have one more question about black holes. You indicated that, or maybe I understood that there are black holes orbiting each other, and in the context of gravitational waves and so forth. Can you expand on that just a little bit?
Yeah, so I mentioned in the previous question how black holes can grow. So they can grow by accreting gas, but they can also grow by merging with one another. And so, especially if you have a lot of very, very big stars that ended their life as a black hole, and they might, and especially if they're very close to one another, because the universe was denser back then, they might be very close together. So they could merge if they get too close. And so we see this happening in our local universe. We see black holes orbiting each other and merging. This might be an event that's even more common in the distant universe, when you have all these black holes and they're very close together. And, that is one potential path of forming very big black holes, is that you have smaller black holes that merge and they become bigger and bigger. And so these events could happen. And so that's potentially what we're trying to see.
Okay, thank you.
Yeah, another question in the room.
I wanted to re-ask Dr. Pickle's question, at least what I perceive it to be. These type 3 stars, the first generations, are fusing hydrogen and helium. Is there enough mass that star has to reach to switch from doing the hydrogen to helium? I know all these later generation stars are doing all these other elements, but that first generation, just looking at the hydrogen and helium, is there enough mass where that tipping point is?
Oh, okay. Thank you for, I understand now. There probably is a mass. I don't know offhand what it would be.
All right. Anybody else with a question in the room? All right. I think that's it. Thank you very much, Dr. Fernandez.
Okay. Thank you for the invitation.